So today we're going to do 64-bit assembly. We did 32-bit last time, and we're just going to do pretty much the same thing in the 64-bit version. So it's a small variation on what we've already done. And I guess I've got to reopen my slides for some reason. All right. Thought I had them, but there's always something. Oh, because I updated them. I re-uploaded them. All right. There are a couple mistakes in the slides. All right. So we'll just go through the same kind of thing we did before, the basics of assembly in 64-bit code. So here's a program. There's an adder function that will take an integer variable and add to it and 2 to it and return it. And here's a main program. It'll set x equals 40, call adder of 2, and then print out the result, which should be 42. All right. So if you obj dump it to look at the assembly code, and you compiled it without a special switch, it'll automatically compile the 64-bit code in a 64-bit operating system, which is pretty much the only kind anybody's using anymore. And if you use obj dump to dump out the assembly code, you'll see it here. And so it looks a lot like the code we saw last time. The only difference is the registers are, instead of being ESP and EBP and so on, you're mostly using the 64-bit registers, which are R. Now you can use 32-bit registers, and it does use 32-bit registers for integers, because remember, integers by default are only 32 bits long. So even though it's 64-bit assembly code, it can use 32-bit registers, and it does. So it puts the, it takes the base pointer -4, which is going to be the location where the incoming parameter goes. When you call a function, the stack above the stack above the stack frame in the calling, and at a lower address, the unused stack is supposed to contain the incoming parameters. So it takes the incoming parameter here from RBP -4 and puts it in EDI, a 32-bit register. Then it takes EAX and puts it there. Right, which is going to be actually, I'm a little confused by this. I guess it must be source destination. Yeah, I'm not sure I entirely understand this. Here's where it adds 2 to it, EAX, and when it returns, EAX is the return value. So this is where it adds 2, and this is where it returns it. I don't know what's going on with EDI. Oh, I do remember. It's coming back to me. In 64-bit assembly code, parameters are not passed on the stack. They're passed in the registers. So EDI is the incoming parameter, and this moves it into that location on the stack. And this moves it in from there into EAX, and this adds 2 and returns. Okay, fair enough. So there's 16 registers, RAX, RBX, and so on. And all of them except for RSP and RBP are general purpose. RSP and RBP are the stack pointer and the frame pointer, just like ESP and EBP are for 32-bit. And RIP is the instruction pointer. So, all right. So, and as I mentioned before, you can refer to the 64-bit register or the 32-bit register, the way we did in 32-bit code. You can even refer to 16 or 8 bits, although that's very uncommon. All right. All right, and so that's the more details of the same thing. All right. So you had an instruction like add 2 to RAX. The opcode is add, 2 and RAX are the operands. 2 is an absolute value, so it must be the source, and RAX must be the destination. All right, memory locations can be written like this. Take RBP and add 8 to it, and then refer to the memory in that address because of the parentheses. All right. And you could also have an immediate memory address if you want to, just specifying it. So here's the examples. If you look at the address, 804 contains CA, and we put FD here, 12 and XE in locations in memory that are 4 bytes big, so these are integers. And here's the registers containing various numbers, and so %RCX is the contents of the register, which is going to be 4. Parentheses RAX is going to be taking RAX as an address and going to that memory location. So it's going to be taking 804 and go to that location and find a CA. $808 is going to be the constant 808. 0x808 is going to be that memory location, 808, and that's going to be FD. and so on. We talked about this is going to be 8 past the address pointed to by RAX. This is going to be RAX plus RCX, which is going to be 804 plus 4, so that will be 808 pointing to FD. All right. 4 times RCX plus RAX. This is how you move forward one word at a time instead of a byte at a time. So it's going to take RAX, which is 804, and add 4 times RCX, which is 4. So that's 16. So that'll take us to 814. And 80C, I'm not sure I believe this one. RAX is 804, and RCX is 4, and you're going to take 4 times, plus 4, pardon me, not times 4, plus 4. Okay, that's why. So 4 plus 4 plus 4, that's 480C. All right, fair enough. And this one is 800. Here's the one I was thinking with the comma starting it. 800, comma, RDX, comma 4. This is the one that's going to count up by 4s. So it's going to take RDX times 4, which is 1. So it's going to get us to 804. All right. Anyway, we talked about this stuff before with 32-bit, and as you can see, it's very much the same in 64-bit. So this is the thing I always use as my touchstone. You cannot write to a constant. So that's how I can tell Intel format from AT&T format, which switches the source and destination operands. You can't move something from both the source and destination, of course. And the scaling factors, when you're multiplying, has to be 1, 2, 4, or 8. All right. You can have a suffix in the instruction. B means you move a byte. W means you move 2 bytes. L means you move 4 bytes, and so on. All right. All right, and so move is the most common instruction. Add and subtract are available too, just like before. Push pushes data on the stack, and pop pops data off the stack. All right, and so let's take a look at adder here. I should have it ready to go here. If I do CH7, all right. All right. So let's look at, this is adder 2. Let's look at adder2.c. All right. So this is the same program we saw before. The main function is going to set a local variable to 40 and call adder2 on it, and adder2 is going to add to it there. So this function, adder2, has no local variables. It has a parameter, but no local variables, so the stack frame will have a size 0. It doesn't need any stack here. All right, so we can debug it. .64-bit version. Get rid of the colors. All right, now break as soon as it enters adder2 and run. And now I can disassemble adder2 to see where I am. And you see I'm right here at the start of it. I haven't executed any of the code inside adder2 yet. I'm ready to enter the prologue and begin preparing the stack frame for this function. So if I look at the registers, I'll see the registers from the calling routine, which are here. RSP is 348, RBP is 360. So the stack has size 18 in hex, which is 16 plus 8, 24 bytes. That's the calling routine, the main routine. Now all right, and that's, the other thing you can notice is that the instruction pointer here points to the start of adder2. A lot of 5s and 139, and that's it, a lot of 5s and 139. So that's the instruction pointer always points to the next instruction to be executed, and I put a breakpoint here so it broke before entering that function. So this is the function prologue, which creates the stack frame for the adder2 subroutine, and this is the epilogue that removes the stack frame and returns to the context of the calling routine, which is main. So, all right, so before entering it, as we saw, the stack frame is 18 big, RSP to RBP, from 60 to 48. And now when we enter the routine, we've done all that. All right, if I do 2 next dies to the next instruction, and then disassemble adder2. See, now I'm down here. I've completed the prologue, so now the Stack frame is prepared for the adder2 subroutine, and I can examine it with info registers. And you will see that RSP and RBP are identical now. The stack frame has size 0 because there are no local variables. All right, and if I look at the stack, 12x colors, and this should be RSP, not ESP. All right, then I will see the top of the stack has the saved RBP and the return pointer. This is RBP, is this thing starting with F's ending around 340. This is the RBP of the calling function, the main routine, and this is the return pointer pointing back to the function, to the command in the calling routine that comes after the one that called this subroutine. All right. So the epilogue will, let me disassemble this again. The epilogue here, pop and return, will restore the RBP to the calling function, and return will pop the address of the next instruction in the calling routine. This is what takes you out of the subroutine back into the calling routine. All right, so there's other arithmetic. You got add, subtract, increment, decrement, multiply, divide, negate, just like before. And you can do bit shifts. You can do an arithmetic shift to the left, which will double integer every time you do it. You can do a logical shift to the left that will just move the bits and fill them in with zeros and right, and same with arithmetic and logical shifts here. And you can do bitwise operations, and, or, XOR, and not, that will just flip the bits one by one. And like I mentioned, this load effective address instruction is still there just to make it easy to do calculations on registers, a sort of roundabout way to do it, as we talked about before. Let's take a look at a Kahoot. It is 7A, and I should have them ready to go, and there we are. All right. All right. Okay, wait a bit more. All right. All right, so what is the stack pointer in a 64-bit system? It's RSP. That's the top of the stack. RBP is the bottom of the stack. All right. What part of a function reserves space for new stack frame? That's the prologue. Good, the first couple of commands. All right, so which command will divide the integer in EAX by 4? You have to shift to the right by 2. Every time you shift to the right, you have the number, so shifting 2 will divide it by 4. Shifting by 4 would divide it by 16. All right, so let's go back to here. Okay, so conditional control and loops are going to be like what we've done before. You can compare two numbers or test them, and you'll get the 0 flag will be set if these two numbers are equal. And therefore, after that, you can, now here's an unconditional jump. To jump, you can either jump to a named location that you assign with a label in your assembly code, or to an address with a star to indicate you wanted to go to an address. And you can jump if the last operation resulted in 0, or if it did not go to 0, with jump equal and jump not equal. And you also have like jump greater than 0, jump less than 0, and so on. So a go-to is here. So here you have an if, else in C. If x is greater than y, go here, else do that. And in the go-to version, you'd have if is this. If x is less than or equal to y, then go down here. Otherwise, go here and then go to 1. Now, this is considered poor C syntax, but this is what you must do in assembler. So if you look at that if statement in assembly, it loads the variables. This is x and y, and then moves one of them into EAX, and then compares the other to EAX. So this is the if statement, which is going to determine which one is greater. And then if it's less than or equal, then you jumped down here, plus 26. If otherwise, you execute this and then jump over that. So you need two of these jump instructions to make up for the fact that you don't really have if or else or the parentheses in assembler. That's how you do this. Under certain conditions, you'll execute this command, and otherwise you'll execute that command, and in both cases you have to go to return, so that means you have to do two jumps. All right, so here's conditional move is another one. You can combine it all. Conditional move only if it's less than or equal to something. This gets rid of the jumps. You prepare it, and then you only do the move if this is true. So the C move LE is a more efficient way to accomplish that task. And normally you leave it to your compiler to decide which way it's going to be written in assembly code. So there's a bunch of conditional move if negative, move if non-negative, move if greater, move if less, and so on. All right, and I mentioned this before, both C loops compile to the same assembly code. You can use a while loop to do something, adding 1 until you add up to n, or you can use a for loop to count from 1 up to n. And since both of those accomplish the same thing, neither while nor for exists in assembler. They're both done this way. So you have a jump here. You prepare all the variables. Then you jump to this plus 33, where you put I somewhere, compare I with n, and only if it's less than or equal, then you jump back here and do what's inside the loop, and you keep going until it fails this test, and the loop keeps adding up numbers and adding 1 to the counter. So that's the structure, and the assembly code is the same for while and for loops. All right, and functions in assembly, this is what confused me right at the start of the lecture. I'd forgotten this. You can leave or call Q and return at the end of a function, which is fine. That will pop the instruction pointer off the stack. And this is what I was meant to saying. In 64-bit code, you no longer pass arguments on the stack. You do that in 32-bit code because there aren't enough registers to use them for this purpose. In 64-bit, you have more registers, so there's just a pattern. The registers enter the function with RDI, RSI, RDX, RCX, R8, R9. So you can have up to 6 parameters without using the stack, and you only use the stack if you have more than 6 parameters in your function. So you almost never do that. All right. So we can look at adder, which is here. All right, let's get out of here and clear and cat adder.c. All right, so this is the one we did before that's going to have data remnants on the stack. So we have a main routine that's going to call assign and then adder. Assign is going to make a local variable with 40, and adder is going to add to a parameter that should have been passed in as an argument but was not. It's going to be left on the stack from before. So that's what happens here, and it's just like before. So I think I'll just go with the pictures. Here you're just about to enter the function, and if you look at the contents of the stack, you can see nothing exciting on there at this point. But when we continue and run through this function, it's going to put this number 28, which is 40 in hexadecimal, on the stack, and you see it down here. It's put that number on the stack, and it did that because it was a local variable in that function. Let's go back. This was assign. If you go back and look at the code, assign here defines a local variable to be 40. So it's in this function stack frame, and everything is working correctly at this point. And when you return, it restores the stack frame with the prologue, but it does not erase the stack that's now free. It just leaves it available for reuse. But when you call the next function, called adder, this is the one that has an error in it. You call adder, and adder returns a plus 20, but it never got any value for a. And instead of just crashing like Go would and saying you didn't define the variable, this is what C keeps doing. C will often continue to run and just do the wrong thing, which is why it has so many security flaws. It will just take whatever value was found on the stack and treat it as a variable, and you'll see it in the assembly code here. So this is adder, and here we are disassembling adder. So it just takes the value based on the base pointer on the stack and copies it into EAX and uses it. The function does not know that the calling routine forgot to place a value there. This is the sort of amnesiac property of C and assembly. This function should be called with a parameter ready to go on the stack, and it doesn't know that the calling function forgot to do that. Instead, it uses the leftover data on the stack, which is this 28. So you get 42 out of it, when it really ought to just give you an error message saying you're using an undefined variable. All right. There's recursion in assembly, as we talked about it before. A function can call itself. That's what this one will do. This is going to sum all the numbers from n to 1. So it's going to call it on n. It will call itself with n minus 1, so it'll count down from n down to 0. And you'll have many copies of the same function in the stack with their own stack frames that will pile them all up, and then they'll all return. And the same thing happens in assembly as it would in C. And you have arrays. Like we said, you can define an array, type a variable, and then array, and then a number of entries. And therefore, it will just add them up. And therefore, you can refer to array sub 0, array sub I, or a pointer to one of the elements, that sort of thing. And if you have 10 integer elements, each one of them is 4 bytes long, so you'll have a total of 40 bytes used for that. And here's the address, 04812, relative to the start of the array. You can also have your matrices we're not going to bother with, but you can also have structures in assembly. So you can have a structure with a 64-character name, a couple of integers, and then a float, and it will just stick them together. Each character in the name will be a single byte. Then you'll have 4 bytes for the integers and some longer range for the floating point value. Don't remember how big floats are. And so you can initialize it here, set them all to values, and in assembly code, you'll just be updating them all with an index counting through the structure here. And, all right. And also, there will be a data alignment. As you say, 4-byte data types are 4-byte aligned. So if you were to have a 63 characters for the name, then you'd have a padding byte here that's not used to make the integers lined up on a 4-byte boundary. And you can have buffer overflows, as we've done before. This is going to be secret. So if we go here, All right. There's a thing here called secret. And you can guess a number, and it says you're wrong, but you can also guess a really long entry, and it will crash. Right. So if you debug it, all right, and get rid of the colors, and run it, and feed in that long number again, then it will crash, and here it'll tell you what was in the instruction pointer, 4B, 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 4C, 4C. So you can get that it's B, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. So the B's are K's, and the C's are L's, so it was these last 6 bytes are what did it. The K's and the L's are what ended up in the instruction pointer. So you can disassemble the end game to find the desired address to go to, and then you can just make a Python code after you get rid of randomization. You can make an exploit code that will just have that address in here backwards, 040, the address you want to go to, and then you can run the win. We've done this before. Some of the data goes in the instruction pointer, so you can carefully point the instruction pointer to run the code that you want to execute. So that's the simplest kind of attack, using return-oriented programming, where you reuse code that the developer actually put there. So address-based layout randomization makes it difficult to jump to addresses of code you jumped in, and stack canaries prevent buffer overflows because they put a random value at the end of where the data is stored in a stack frame and before the return pointer is. So if that number changes, the program halts, which means you cannot overflow and rewrite the return pointer. You can't get away with it. This is a powerful defense. And data execution prevention is another useful defense. If you look in this program here, for example, into info proc mapping, you will see the memory regions that are allocated for this program to use. And secret has the first 3, and you can see this one is readable, but not writable and executable. This is the text section. It has executable code. This is readable but not writable. These are immutable variables. This is the stack. You can read and write on it, but you cannot execute it. That's the point. Modern operating systems will only let you have write or execute, but never both at once. So you can't have a place where data comes in and gets written and then later execute it. Not without defeating this defense. All right. All right. And all right. And so you can also quit using the dangerous C functions that make buffer overflows. Instead of using getfs, you use fgetS that has a limit. And these don't really, in practice, prevent buffer overflows because it's easy for programmers to make mistakes. But they help. These functions all allow you to specify how many bytes to read instead of just reading to the end of the input, which is dangerous. So if you correctly use them, it will not read more than you've reserved memory for. And so here's the safer source code for this one, where when you enter the secret number, instead of letting me put in a long number, you only read the first 12 characters of what comes in and no more. And so then you can put in as long as you want, and it will not crash. It will just say you're wrong. All right. So let's take a look at another Kahoot, which is 7B. right, so where are the parameters placed when you call a function in 64-bit code? Yep, they're moved in registers. In 32-bit code, they're moved on the stack, but in 64-bit code, they're moved in registers. All right, how long is a pointer to an array in a 64-bit Intel system? The addresses are all 64 bits long. That's the point of a 64-bit system. And one of the reasons why we've all switched to them is because 32-bit systems can only index 4 gigs of RAM, and we want more than that. So we use 64 bits, which can index an unthinkable huge amount of RAM. All right, what Linux command will show a file in hexadecimal and ASCII? I use it quite a lot in the projects. XXD, quite useful. Lets you view the raw contents of a file in hex and ASCII. It's very useful when you're doing a buffer overflow exploit and you have some unprintable characters. Good. All right. Well, that's it for the PowerPoint.